r is a function of theta. So when the way we think about polar coordinates, even though we write r comma theta, we think this first, and then as at every given theta, there's some value of r. So independent, dependent, and that's how we were practicing plotting points, right? Independence theta, that comes first for every value of theta, or for a value of theta, you're picking you're plotting r, the distance from the pole, and so that goes along with our polar graphs, which we have this form, and so this would be an example of that. R equals 1/2 theta. So what does this mean? So we're talking about a set of points that we're going to plot in the polar plane, right? Just like we've graphed a zillion graphs, y is a function of x. But now this is in the polar plane, so theta is our angle swept counterclockwise from the x-axis, and then r depends on that. Okay, so we think about theta increasing. Oops, that's. Okay, so we think about theta increasing. So here's our theta angle increasing. And so now for this particular set of points, the value of theta, the value of r is always 1/2 of theta. So what will r do as theta increases? If r is always 1/2 of theta, what will the general variation of r be as we turn counterclockwise?
It would also increase, would it not?
Okay, so he's saying that r will increase as theta increases. So as we turn in a counterclockwise circle, r will increase with it. R will increase. Do you agree with that? Does everyone agree with that?
Yeah, but to clarify, it increases half as much as theta.
Okay, well, so yes, but I just want to get the general idea here before we get to that. So yes, r is going to increase as theta increases. So what I want you to imagine in your mind's eye, look at the positive theta axis here, and as I turn it counterclockwise, I want you to imagine simultaneously moving out away, right? R increasing means moving away from the pole. So these two things are happening at the same time. We're turning counterclockwise, and we're generating points by moving away from the pole along that axis. So I want you to imagine that in your mind's eye. Imagine that in your mind's eye. Increasing r, moving away from the origin or the pole as theta increases. One more time. What would that be like? Start at the pole. Now, as I increase theta, you imagine moving away from the pole as theta increases. So now I want to show you and see if this is what you imagined. Okay, I'm going to show you points now, and you see if this is what you imagined when you did that. Ready? Watch. Is this what you imagined? That's r increasing with theta. Show it again. So here's theta equals 0. Theta equals 0. Here's r increasing as theta increases. See that? So we're getting farther away from the pole as we turn counterclockwise. One more time. It's really important to see. This is totally different graphing than y and x, right? Totally different graphing than y is a function of x, so we got to get used to it. As we turn counterclockwise, r constantly increases. Does everyone see it? Does it make sense? So when we reach, when we reach pi over 2, what is the value of r at pi over 2?
Pi over 4.
Pi over 4, which is what? About 3/4? A little bit more than 3/4? So when we reach pi over 2, we're going to be a little bit more than 3/4 of a unit away. So this is pi over 2, right? This direction of pi over 2. And so then at pi over 2, we're going to be a little bit more than 3/4 of the way. And then along the way, what? So 0, and then imagine as theta increases, R increases, right? So for as theta increases, we get further and further away from the pole. And so that will continue, right? So just think, I'll just draw them on these. So I'm drawing. This isn't exactly the graph, but the point is, on every one of these theta values, my R value is greater than it was before. This is R increasing with theta. Does it make sense? So let's show that. Let's show the points and the graph being generated then. For R is 1/2 of theta. Am I at 0? I'm at 0. So here it goes. Watch. Now it's not going to be exactly what I did, but that's the idea. Here we go. Ready? As theta increases, R increases. Now we were way off. What happened? I am graphing R equals 1/2 theta, so what is the problem with pi over 2?
I think.
Oh, I'm doing theta. Sorry. I have the wrong function here. Now let's try. There we go. There we go. So there it is. At pi over 2, we're a little bit greater than 3/4. So I just put it in the wrong place. But there's pi over 4, like 0.8 or something. Okay, questions on this? All right, what is dr d theta? What is dr d theta? For this graph?
1/2.
1/2. So I have a rate of change dr d theta equals 1/2. We're getting to the end of the semester. What does it mean? What does the value 1/2 mean? 1/2 means what? And we're all, your TAs and I are all hoping and praying that a vast majority of you could give a good explanation of what that number 1/2 means.
As theta increases, R increases 1/2 times theta.
Okay, pretty good. Anybody else want to try it in their own words? Yep, pretty good.
I would say it increases 1/2 the change in theta.
So start from the beginning.
So for every small change in, like dr is equal to 1/2 the change in theta.
Right, so given a small change in theta, d theta, what? The change in R is? Is what?
Half.
Half. Is it half? The change in R is a half?
Times the d theta.
Right. Given any small change in theta, the resulting change in R is half as much as the change in theta. Okay? Is that a positive rate or a negative rate? Of course, it's a positive rate of change. And so what does a positive rate of change mean? What does that mean for values of R?
It's increasing.
Yeah, that means that R is increasing. Okay? And so how do we see that in this graph? So now looking at the purple graph. Now that the purple graph has been generated, we generated it covariationally, R as a function of theta. How do we see that the rate of change is positive or R is increasing? How is that seen in this purple graph?
The distance from the pole of the graph is getting bigger and bigger.
Okay, good. Okay, excellent. What about at a particular value of theta? So if I pick this value of theta, I'm going to pick this value of theta right here. I just want to focus in right there on that value of theta. And this point of the graph. Looking just in that local vicinity, how do I know that the rate of change is positive?
The radius of the points before it were smaller, and
Okay.
then the radius of the points in front of it would be larger, so you know that
Good.
you're moving in the direction that you would be as you move counterclockwise, that your radius is increasing.
Good. All right. Yeah. So you think as we move counterclockwise around that point, do you see that the R value is increasing? What would a rate of change of 0 look like? What would rate of change of 0 look like at this point?
A circle?
Yeah, it'd be along this circle. Do you see this? So I'm going to draw it as a dotted line. Do you see along that circle right there? That would be dr theta of 0. That'd be a constant, or a no change, right? No change in R if you stayed on that circle. So that dotted line represents dr d theta equals 0. And so now comparing the purple line to the dotted line, you see that for angles less than, the radius is less, and for angles greater than, the radius is more. And so can you see in your mind's eye that that's an increasing R and therefore positive rate of change compared to the dotted line, right? Lesser R, increasing R, which means you go farther from the pole compared to this dotted line, right? Compared to that dotted line that's staying the same distance from the pole, or a rate of change of 0. As you move through that point, you're getting farther away from the pole.
And so our direction for these are always counterclockwise?
Yes, increasing theta is counterclockwise. Increasing theta. To make theta bigger, you go around counterclockwise. Okay, so does this make sense? All right, let's practice. So, this has a constant rate of change of 1/2, which means we could do what we just did for any angle. Do it for this one, say. Do you see that R is increasing at that point? Compare it to constant R. There's constant R, the dotted line. Right, that's constant. I'm trying to draw along that. There's constant R. Notice that before the radius is less, after the radius is greater. So this is increasing, getting further from the pole at that point. That pink graph is getting further from the pole. And so again, that's that positive rate of change. R is increasing. Okay, practice. Okay, so these are all like parts of a polar graph. So imagine you're turning counterclockwise, and this is like part of a polar graph is what I'm drawing here. So it would keep going on either end, but we're just analyzing, say, somewhere in the middle there. So these are all parts of different polar graphs. Okay, so do these all have the same rate of change or different rates of change?
Different rates of change.
Someone's saying different. How do they have the same rate of change? Is it possible that they have the same rate of change?
If you were to plot it on a Cartesian graph, they would all have the same slopes.
Right. So in terms of dy dx, all the same. And about what? About what slope is that, would you say?
-2-ish.
-2-ish. -2.5 maybe. Yeah, exactly. -2-ish. All right, but now in polar, this is totally different, right? So I want you to, so for each one of these, F1 through F8, we're going to say, is dr d theta very negative? Just negative? Close to 0? Positive or really big positive? So we're going to analyze it. We're pretending that each one of these is a little part of some bigger polar graph. And at the, kind of at the middle of that, at the middle of that little plot of points, near the middle, is dr d theta kind of a big negative, just a moderate or small negative, close to 0, positive, or very large positive? So let's do F1 together. How about F1? So what about F1? What would you say? Hey, Ryan, your microphone is on. Ryan Ling. Hey, Ryan Ling, your microphone is on.
Sorry about that.
Okay. So what about F1? What would you say? Really big negative, negative, 0, positive, really big positive. What would you say for F1?
Negative.
Someone wants negative. As theta increases, is R decreasing? That's what, by saying that that's negative, you're saying R is decreasing. Agree?
I think it's negative too, yeah.
Yep.
I agree.
Yeah.
Good. So for F1, R prime less than 0. Okay, F2. What do you think for that one?
Positive, maybe very positive.
Okay. Someone wants positive. Others agree positive?
Yeah.
Yeah, I agree.
Yeah. So now here, as theta increases, right? As theta increases, your R going this way. R is getting bigger. R prime positive. How about F3?
Very positive.
Positive.
Very positive, right? So for a little change in theta, R is increasing rapidly, going counterclockwise. Is everyone following this? This is what rate of change means in polar coordinates.
Yes.
Big positive. All right, how about F4?
Very
Negative.
negative.
Negative. And we could sit here and argue. We could argue if that's just negative or greatly negative. But the point is it's negative. Okay, F5.
Negative.
Negative?
Pretty close to 0.
Yeah, this is pretty, that's what I was going for anyway. So, at this point right here, pretty close to 0. That as we turn counterclockwise this way, R is staying the same through there. So it might be a little negative here, a little negative on this side, positive on this side, but at kind of the middle, there's a place there where it's 0. The rate of change is 0. How about F6?
In positive.
Positive. F7.
Very positive.
Yeah, very positive, or maybe like undefined, like because it's like we're increasing R without changing theta. So this is maybe like an undefined case, right? If you're staying on a theta line, then your rate of change is it's so big that it's undefined. Kind of like a vertical line in y equals x, right? Because as theta changes, R is increasing without theta changing. That's like undefined. All right, what about F8?
Would that be very negative?
Yeah, I would think that would be very negative, right? So as you're going counterclockwise, R is decreasing pretty rapidly there. All right, questions on this? So we're going to start sketching polar graphs, and this is going to be one piece of the puzzle to sketch polar graphs. Is going to be looking at, eyeballing rate of change and letting that help us, fine-tune a polar graph. It's by using rate of change. Any questions on how rate of change shows up in polar graphs? Okay, so let's do this is cool stuff. Let's do R equals 2 sine theta. So we've seen R equals 1/2 theta. That was kind of our first graph. You saw, and you saw in recitation, you saw constant R's. So those are important. So we've seen, R is a constant, and that's just a circle centered at the pole, right? For all theta, you just state the same R value. And then we've seen R equals 1/2 theta. And we saw R just constantly increased as theta increased, and so it made like a spiral, and a growing spiral. So let's try so oftentimes these polar functions will involve trig functions, and they make for really interesting graphs. So let's do that. So let's do R equals 2 sine theta.
For all of these, are we going to be going in the counterclockwise direction?
Yeah, because theta increases. Increasing theta is counterclockwise. So we're always going to think about increasing theta. Little change in theta means theta is increasing. So it will just be too confusing if then we start also doing clockwise. So increasing theta is counterclockwise. So that's how we'll always sketch these graphs.
Thank you.
Yeah. Okay, here we go. So now we're going to do R equals 2 sine theta. And so here's the technique for sketching these graphs. Okay, so yes, we're going to use the rate of change a little bit, but the main thing is we're going to first start by sketching R as a function of theta in rectangular coordinates. So R is our vertical axis, theta on the horizontal axis. And then we're going to use the Cartesian graph of R as a function of theta to sketch the polar graph. This Cartesian graph is going to help us think covariationally, meaning we're going to think as theta changes, right? As theta increases, which is counterclockwise rotation down here, what is R doing? Okay, so here's the strategy for sketching polar graphs. We're going to sketch R as a function of theta in rectangular Cartesian coordinates, sine curves, cosine curves. And we're going to use that sketch to sketch the polar graph. Okay, so what does R equals 2 sine theta look like? So we know theta has 2 sine theta. 2 sine theta has a period of 2 pi. So we know that cycles of cosine and sine are broken up into fourths, right? So what does 2 sine theta look like? So we know there's a max for these sine and cosine graphs, and a min and a midline. So we got the midline, and what is the max and min of 2 sine theta? What's the max?
2 and -2.
Okay, and where does 2 sine theta start its cycle? Does it start at the max, the midline, or the min?
Midline.
Starts at the midline. Sine starts at the midline, and then does it go from the midline? Does it go up or down?
Up.
It goes up to the max in the first quarter. It goes back to the midline in the second quarter, down to the min in the third quarter of the cycle, and back to the midline to finish the cycle. And then it will keep going. Okay, so now we're going to use this graph to sketch in polar coordinates. So what do we got? We got R increasing, right? So R is increasing from as theta increases from 0 to pi over 2. What does R do? Looking at the graph. So as theta increases from 0 to pi over 2, what does R do?
From
R
0
goes
to
from 0 to 2.
0 to 2. Okay? And then let's think about the rate. Is the rate starts, what is the rate? First of all, positive or negative as we do that?
Positive.
Positive. Is it getting less positive or more positive or staying the same, the rate?
It gets less positive.
Less positive, right? It's the greatest at the beginning, and then towards the end, the rate is much less, right? So that means we're going to be starting at 0, and we're going to shoot out from the origin quickly, and then as we close and increase, r is going to increase. And then as we reach pi over 2, it's going to kind of level off in terms of kind of become tangent to a circle, right? So a less of a rate of change. So can you imagine that? So, so now I want to graph 2 sine theta. So imagine what that will be like. As theta increases counterclockwise, starting at 0, r is increasing greatly, and then less as we move, and we're going to reach what point at pi over 2? R equals 2, right?
2.
So we're going to start at 0. So imagine r increasing rapidly at first and then slowly as we turn from 0 to pi over 2. Imagine r increasing rapidly, shooting out the theta ray, and then increasing slowly at the end to reach 2. Can you imagine that with your mind's eye? So here's what you should be imagining. I'm going to turn on the point, see if you imagine this. So r increasing rapidly at first, then increasing more slowly until we reach 2. Did you see the point? Did you catch it? So as theta increases from 0 to pi over 2, we're turning counterclockwise. R increases rapidly, high rate of change, then decreasing rate, but r is increasing to 2. I'm going to turn on the graph now. You're going to have to sketch these by hand. So you need this mental, that what I'm trying to have you practice in your mind's eye is going to be crucial to draw the sketches correctly. Watch. R increases rapidly at first, then keeps increasing, but more slowly until the rate of change. What's the rate of change at pi over 2?
0.
Yeah, so at 2, you'll be parallel to the circle of radius 2 because the rate of change is 0 at the top. Does it make sense? So then what happens from pi over 2 to pi? What happens to r?
R decreases.
From 2 to 0. How does it decrease at first? Slowly at first, and then as we reach pi, decreases rapidly back to 0. So this is really going to be symmetric, right? It's going to kind of undo what it did in the first quadrant. It's going to decrease slowly and then more rapidly until it reaches 0. Can you imagine that? Decreasing slowly, decreasing rapidly, more rapidly until it reaches 0. Okay, so what about now? What happens now? So now r as we go from pi to 3 pi over 2, r does what?
Decreases.
Decreases. Decreases from 0 to negative 2. So we imagine theta is increasing through here. So imagine theta is decreasing through here like this. This is my theta. Theta's doing this. What would it be for r to be negative and increasingly negative? Where would that be? It'd be back in the first quadrant, right? So as my theta turns here through the third quadrant, my r is going to be 0 and increase to negative 2. So where is negative 2? I should turn off the axes here. That's better. Okay, where at 3 pi over 2, where's negative 2? Here's positive 2 at 3 pi over 2. So negative 2 is going to be this point, which you've already graphed. So as theta turns through the third quadrant, r is going to be negative, increasing rapidly and then more slowly. Well, that's going to be exactly what we did before. It's just going to repeat the same set of locations. Watch. So this is now r increasing getting more, decreasing rapidly and negative, and then decreasing more slowly and negative until it reaches -2. So here's, we're at 3 pi over 2, we reach -2. So this part, for this graph, these points are just repeating the same locations we had in the first quadrant. And then similarly, we're going to go back from -2 back to 0. At first, slowly, and then rapidly going back to 0. So the second part of the cycle for 2 sine theta in the polar graph just repeats the same locations as the first half. So that means this polar graph, this has a period of 2 pi in rectangular coordinates, so period. But has a period of pi in polar coordinates, because once you reach pi, you've graphed the whole thing, and now you're going to start over again. And so every graph will be different. Sometimes polar graphs will have the same period as the Cartesian graph. Sometimes the period of the polar graph will be bigger than the period of the Cartesian graph. Who are you? Go away. So this is not always the case. So with every polar graph, the comparison of the period to rectangular coordinates and polar coordinates will be different. There won't be this rule for that. In this case, our polar cycle is half as long as the rectangular cycle. Okay, questions on sketching this graph. And what do? We graphed r equals sine 2 theta in rectangular coordinates. We use the rectangular graph to sketch the polar graph by thinking about covariation. As theta increases, how does r increase? And then we also look at the rate of change of the graph too to help us.
So the points in the third, the points that, like, if they were positive, they would show up in the third quadrant.
Yeah, if r was, yeah, so like if, yeah, if we did this, like the absolute value of 2 sine theta, then we'd have that graph there, and those r's would be positive, so then we'd be in the third quadrant. Yeah, does that answer?
Sorry, it would make the same graph as the blue circle, just in the bottom, if it was absolute value.
Yeah, if it's absolute value, yep. We would get this, so now it's the same as this, but now r's are positive, and r is positive in the third and fourth quadrants down here.
Right. Okay, thank you. That makes sense.
Sure, good. All right.
Professor,
Yeah.
really quick. Explain to me the reasoning one more time why the negative part of the sine graph in Cartesian is still positive. It's still positive in polar.
Okay, so
Like
in the third
where's this
quadrant, where
Yes.
in the third quadrant, where are negative values of r? So here we are in the third quadrant.
Oh, I see. Okay, so it's
So in the third quadrant, to plot points for negative r's, that's back here. That's to here.
Right. So
So you imagine.
since R is
Imagine, so r is 0, and now r is going to get negative and more negative. Watch the point. R is getting more and more negative as we increase to 3 pi over 2 until it reaches -2. Now r is -2, and now r is going to get less negative. So that's in the second quadrant, coming back to 0.
see now. Thank you.
Okay, so let's take a look at that. What does that look like?
Circle.
It sure looks like a circle. Now, do we know for sure it's a circle? Well, we'd have to show it mathematically. So, is it a circle? So, what do we know about? So, can we change this to an equation of x and y? And if we follow all the, if we do the algebra correctly and we get an equation of x and y, that can tell us if this is a circle or not, because we know in x and y, we know what equations of circles look like as equations of x and y. So how are we going to do that? So we got to go back and review that x is what in polar coordinates and y is what in polar coordinates?
Our cosine theta.
Our cosine theta, our sine theta, and then we had another relationship between x, y, and r. What was the other relationship?
R squared equals x squared plus y squared.
Right, x squared plus y squared equals r squared. So we're going to use these, which are true for all values of theta, to transfer this. So, I got 2 sine theta. It'd sure be nice if I had what? Instead of, that's something close to something that would be nice. What would be nicer to have? 2 what?
2r sine theta.
Yeah, it sure be nice to have 2r sine theta. But I got to maintain this equality. I want to keep this equation. So therefore, on this side I have?
R squared.
Well, so now this is really nice, right? Because what's 2r sine theta?
2y.
2y. What's r squared?
X squared plus y squared.
Look at that. So r equals 2 sine theta is equivalent to x squared plus y squared equals 2y. If we do the math, we got x squared plus y squared minus 2y equals 0. We're thinking circle. What do we need to do here?
Complete the square.
Complete the square. We take half of the linear coefficient and square it. What's half of -2? -1 squared. -1 squared is 1. That completes the square, and my perfect square is y minus 1 squared. And lo and behold, I have a circle of center what?
Center 0, 1.
0, 1. Radius?
1.
So let's do capital R. Is that the circle I have? Center 0, 1. Check. Radius 1. Check. Got it. So this circle, radius 1, center 0, 1, is equivalent, the equivalent set of points to r equals 2 sine theta, and we showed it algebraically.
Where did you get that 1 after you subtracted
Completing the
two
square.
line above?
Completing the square. You take half of the linear term squared. That's called completing the square. You take half of the linear coefficient and square it, and that will complete the square so that we can write it as a perfect square binomial like this. So, but if I add it to here, I got to add it to here as well to keep the equation. Remember doing that? You did that at some point in your math career. You've done that, if you remember. So
we did prove that it's a circle?
Yeah.
Or
That proves that this is truly a circle.
Oh, okay. I wasn't sure what we were.
Yeah, because we followed all the math rules here, and we got an equivalent equation. We know that equation is a circle, so therefore this is a circle.
Yeah. Very cool. Thank you.
Yeah. Okay, so along those same lines, let's take a look at this line, y equals -3, this is a new problem, the line y equals -3x plus 2. So I want to write this, so similar to how we took this polar graph and we wrote it as an x and y equation, I want to take this x and y equation and see if I can come up with a polar graph for it. So what is y equal to?
R sine theta.
X is?
R cosine theta.
And so what am I looking for? R as a function of theta, which means I want to solve for r. Get r on the left and get all thetas on the right. So that means I could move this over. Move this over to this side, and then factor out an r. So can I do that all in one step? So I added this over here, factored out an r, and that gives me sine theta plus 3 cosine theta. And I'm one step away, so r equals what? 2 over sine, does that show up still? Maybe not. 2 divided by sine theta plus 3 cosine theta. So how's that? That a user-friendly equation in polar coordinates? 2 divided by sine theta plus 3 cosine theta.
No, it's gross.
Yeah, right, it's gross. Well, that's the point. Lines are not well suited to polar coordinates. The lines that are, oblique like this. The only lines that are kind of well suited to polar coordinates are constant theta values, right? These radial lines. But lines, 3x, where's 3x plus 2? Here's 2. Negative 3x plus 2 is something like this, right? That's not well suited to polar coordinates. So therefore, the equation you get in polar coordinates is not, it's not nice and friendly, right? But if I put that in, watch, if I put in that equation, watch what happens. So I put in 2 divided by sine theta haste makes waste. Sine theta plus 3 cosine theta. Okay. And let's turn that on. There it is. So I just graphed 2 over sine theta plus 3 cosine theta. And there it is. It goes through the point 0, 2. And it has a Cartesian slope of negative 3.